We talked about ideal gases. Now we're going to talk about real gases. So in an ideal gas, there are no attractions between gas particles, and the gas particles themselves have essentially zero volume. Real gases act much like ideal gases under kind of normal, moderate circumstances. So at standard temperature and pressure, real gases behave very closely to what we expect from ideal gases. So here we have a comparison. The molar volume of an ideal gas is 24.41 liters. We calculated that the other day. So here are several real gases. At STP, you measure the volume of 1 mole, and these numbers are close to the 22.41. So these gases are behaving very close to ideal gases. But when we get to high pressure or low temperature, then the behavior deviates from ideal behavior. So let's look at low pressure. Under low pressure, the molar volume of argon is nearly identical to that of an ideal gas, but if we increase the pressure, we're squeezing those molecules, those atoms, closer and closer together. The molar volume now becomes greater than predicted by the ideal gas law. And what happens here is that as the volume of the gas gets smaller and smaller, the volume of the individual atoms begins to become more important. So like, the people in Wyoming, the size of the individuals doesn't matter so much, but you get 10 people on an elevator, now the size of the individuals matters a lot, right? So as we get the molecules or atoms closer and closer together, their size begins to matter more. And so this causes a real gas's volume to be higher than expected. So here we have molar volume versus pressure for an ideal gas in red and for argon in green. At low pressures, they're the same. But as the pressure increases, the deviation grows and argon's volume is higher than predicted because the volume of the argon atoms becomes significant. Does that make sense? I got one nod, so that's good. Nobody was shaking their head. This can be quantified, and Johann van der Waals did this in 1873. He modified the ideal gas equation to fit the behavior of real gases at high pressure. So the volume increases, and so he took the ideal gas law and he added a factor to compensate for real gas behavior. The B there is called a van der Waals constant, and it's going to be different for every gas because every gas has particles that are of different sizes. And the amount of change there is also dependent on the moles of that gas. Temperature also affects the behavior. At high temperatures, the pressure of a gas is nearly identical to that of an ideal gas. And this is because as those particles are moving quickly at high temperatures, when they collide with each other, they do so very quickly and they don't have a chance to interact with each other. At low temperatures, we see that the pressure of a gas is less than predicted. What happens here is that as the particles are moving more slowly, when they collide with each other, they have a chance to interact with each other. And there are attractive forces between gas particles. So at low temperatures, those particles become more significant. They spend more time interacting with each other, less time colliding with the walls, and so the pressure is less. And those forces of attraction are called intermolecular forces or intermolecular attractions, and we'll learn a lot more about those in another chapter. So here's a graph showing that effect. Here we're looking at the pressure of a gas versus the temperature. And we see for xenon at low temperatures, the pressure is less than what's predicted by the ideal gas law. And that's because the xenon atoms are interacting with each other. So van der Waals also modified the ideal gas law to account for this, A is another van der Waals constant, again, different for every gas. And so this modification, you subtract A times n squared over v squared. And that can be used to compensate for this behavior. So you can combine both of those factors into one big messy thing. So here we have the correction for intermolecular forces. Here we have the correction for particle volume. And those constants, A and B, would be, you'd look those up in a table. And so you can use this equation, the van der Waals equation, to accurately calculate the behavior of real gases. So the good news is we don't have to do any calculations with this silly equation. We just need to know that it exists. So here we've got PV over RT. What does PV over RT equal? The number of moles. And we're graphing that versus pressure. So for an ideal gas, PV over RT, here this is 1 mole of each of these gases. PV over RT is always the same, it's just 1. But real gases, the behavior will vary. And so what we see is for gases like helium and neon, their line or their curve is above. It's higher than predicted. And this tells us that the most important factor here is molecular volume because, well, just, yeah. So the big effect is molecular volume. Ones that dip below, this is telling us that the intermolecular attractions are the biggest factor. And so we see for xenon that at lower pressures, the intermolecular attractions are significant, but at higher pressures, it's the volume of the atom that becomes significant. For water has significant intermolecular forces, and so over all pressures, this value is lower than expected because of those intermolecular forces. Any questions?